Picture this. Right now, as you're listening to these words, radio waves from distant corners of the universe are washing over Earth. They're passing through your body, through the walls around you, through everything. Most of them are just the background hum of the cosmos, the radio whisper of neutron stars and black holes, of galaxies in their slow cosmic dance. But some of them are different. Some of them arrive in bursts so powerful they outshine entire galaxies for a fraction of a second. Some arrive as narrow-band signals that, if they originated from Earth, we'd immediately recognize as artificial transmissions. And we're catching them, thousands of them, every single day. Since the first modern search for extraterrestrial intelligence began in 1960, we've accumulated an enormous catalog of mysterious signals from space. Hundreds of fast radio bursts have been definitively catalogued. Dozens of SETI candidate signals have been flagged by our most advanced detection systems. The CHIME telescope alone detected more than 500 new fast radio bursts in its first year of operation. Breakthrough Listen has processed candidate signals numbering in the thousands from galaxy surveys. And yet, despite this wealth of detections, despite the sophisticated technology we've deployed, despite decades of searching, we haven't confirmed a single signal as definitively originating from alien technology. The question isn't whether we're receiving signals. We absolutely are. The question is what they are, where they come from, and why nearly all of them get filtered out, set aside, or lost in the overwhelming static of human-generated radio interference. This is the story of the signals we've detected, the ones we've pursued, and the fascinating reasons why most of them end up being ignored or explained away. It's a story about the challenge of finding a cosmic needle in an electromagnetic haystack, about the surprising discoveries we've made along the way, and about what these mysterious transmissions are teaching us about the universe itself. Before we dive into the thousands of signals we've detected, we need to understand where this all began. The search for extraterrestrial intelligence has a precise birthday. On April 8, 1960, astronomer Frank Drake pointed the 26-meter radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. For 150 hours across multiple sessions, Drake listened with a simple receiver capable of monitoring a narrow band around 1420 MHz, the frequency of neutral hydrogen emission. This was Project Ozma, named after the princess in L. Frank Baum's Oz books. Drake heard nothing except for one false positive that turned out to be a passing airplane. But Project Ozma established the methodology that would define SETI for decades to come. Look at nearby stars. Listen at frequencies where artificial signals would stand out against the cosmic background. Hope that someone out there is transmitting. The reasoning was elegant in its simplicity. If we had radio telescopes and transmitters, other technological civilizations probably would too. Radio waves travel at the speed of light, the cosmic speed limit, making them ideal for interstellar communication compared to sending physical probes. And the universe is transparent to radio waves in ways it isn't to other forms of electromagnetic radiation. That same year, Drake proposed what's now called the Drake equation, a way to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually develops, the fraction where intelligent life emerges, the fraction that develops technology detectable across interstellar distances, and the length of time such civilizations remain detectable. It's less a tool for generating specific predictions and more a framework for thinking about the problem. Depending on the values you assign to these largely unknown factors, you could conclude there are millions of detectable civilizations or that we're utterly alone. But Drake's pioneering work established something crucial for everything that followed. The universe contains roughly 100 billion stars in our galaxy alone, and there are perhaps 2 trillion galaxies in the observable universe. Even a tiny probability of technological civilizations existing adds up to enormous numbers when multiplied across such vast scales. The mathematical argument for searching was compelling. It still is. The early years of SETI were characterized by sporadic, underfunded searches. Various projects came and went. The Ohio State University Big Ear Radio Telescope conducted a decades-long search starting in the 1970s. Harvard's META project, funded partially by the Planetary Society, scanned 8 million frequency channels simultaneously starting in 1985, finding 37 candidate events over a decade of operation, none of which ever repeated. Australia launched similar efforts. The Soviet Union had its own SETI programs. But these were modest affairs by today's standards, limited by the technology of their time and chronically starved for resources. Everything changed with the advent of powerful digital signal processing and the realization that ordinary people could contribute their computer's idle processing power to the search. SETI@Home launched in 1999, allowing millions of volunteers to analyze data from the Arecibo Observatory's radio telescope. By 2009, the project had over 180,000 active participants, contributing 290,000 computers with a combined power of 617 teraflops. For the first time, SETI had truly massive computational resources. And with those resources came the ability to search through far more data, looking for far more subtle signal types than ever before possible. The modern era of SETI arrived in 2015 with the announcement of Breakthrough Listen, a 10-year, $100 million initiative funded by technology investor Yuri Milner. This wasn't a shoestring operation cobbled together with spare telescope time and volunteer labor. This was a comprehensive, professionally staffed program with access to the world's most powerful radio telescopes. Breakthrough Listen would survey 1 million nearby stars, scan the galactic plane, and observe the centers of 100 nearby galaxies. It would look for radio signals and optical laser pulses. All data would be made publicly available for anyone to analyze. This was SETI at a scale and with resources that Frank Drake could never have imagined back in 1960. But Breakthrough Listen wasn't the only game in town. Fast radio bursts had been discovered in 2007, and by the 2010s they were becoming a major focus of radio astronomy. These weren't SETI signals in the traditional sense. They weren't narrow-band transmissions that looked artificial. They were something else entirely. Powerful, broadband bursts of radio energy lasting mere milliseconds, arriving from billions of light-years away, releasing as much energy in 1,000th of a second as the sun emits in a year or more. No one knew what caused them. Some speculated they could be artificial. Others proposed natural sources like magnetars or colliding neutron stars. Either way, they needed investigation. And so, by the late 2010s and early 2020s, we had multiple overlapping efforts all detecting various types of signals from space. SETI projects looking for potential technosignatures. Fast radio burst surveys cataloging these mysterious cosmic flashes. Optical SETI programs scanning for laser pulses. The volume of data being collected was staggering. Petabytes of observations, millions of signal detections, thousands of candidates flagged for further study. The challenge was no longer detecting signals. The challenge was figuring out which ones mattered. To understand why most signals get ignored, we first need to understand what we're detecting. When we talk about signals from space, we're really talking about several different categories of phenomena, each with its own characteristics, detection methods, and interpretations. First, there are narrowband radio signals. These are what traditional SETI primarily searches for. A narrowband signal is one that concentrates its power into a very small range of frequencies. Think of it like a laser pointer versus a flashlight. A flashlight spreads its light across a broad area. A laser pointer focuses all that energy into a tight beam. Narrowband radio signals are the laser pointer equivalent for radio waves. They're special because nature doesn't typically produce them. Natural astrophysical processes generate radio waves too, but they're almost always broadband, spread across wide frequency ranges. A narrowband signal, especially one that's drifting in frequency over time due to the Doppler effect from relative motion, looks suspicious. It looks potentially artificial. The narrowest natural radio emission we know of comes from astrophysical masers, which can have bandwidths around 1 kHz. But SETI searchers often look for signals less than 10 Hz wide, sometimes just a few hertz. For context, commercial FM radio stations transmit with bandwidths of about 200,000 Hz. A signal only a few hertz wide is extraordinarily focused. If we detected such a signal from space, and it wasn't radio frequency interference from human technology, it would be hard to explain with natural processes. This is why narrowband signals are SETI's primary target. But detecting a narrowband signal isn't straightforward. Radio telescopes don't just receive a single frequency. They sample enormous bandwidths, often several gigahertz, covering hundreds of millions or even billions of individual frequency channels simultaneously. The breakthrough listen instruments on the Green Bank telescope, for example, record 6 gigahertz of bandwidth at once. That's like monitoring over 800 million radio channels simultaneously, each only a few hertz wide. The data rate is staggering. 24 gigabytes per second. In a single day of observation, you generate more data than a human could possibly examine by hand in years. This is where algorithms come in, sifting through this flood of data to flag anything that looks interesting based on specific criteria. The criteria matter enormously. A true extraterrestrial signal should appear when you point your telescope at a specific target and disappear when you point away. It should have a Doppler drift, a change in frequency over time because the transmitter and receiver are in motion relative to each other. The Earth is rotating, orbiting the Sun is orbiting the galactic center, and if there's a transmitter on a planet somewhere, that planet is rotating and orbiting its star too. All this motion adds up to frequency drift. The signal shouldn't repeat at intervals that match human technology, like the 60 Hz cycle of electrical power or the common oscillator frequencies used in electronics. These are the kinds of tests algorithms apply to millions of signal detections to winnow down the list to a manageable number of candidates. Then there are fast radio bursts, a completely different beast. Fast radio bursts were discovered by accident in 2007 when astronomer Duncan Lorimer and his student David Narkovich were examining old archival data from the Parkes radio telescope in Australia. They found a signal that lasted less than 5 milliseconds, was incredibly bright at 30 Janskis, and had a dispersion measure indicating it came from well outside our galaxy, possibly a billion light-years away or more. This was unlike anything anyone had seen before. The burst released an enormous amount of energy in an extraordinarily short time. It didn't repeat. It just flashed once and was gone. For years, fast radio bursts remained rare curiosities. Only a handful were known, and they were all one-time events detected in archival data, impossible to follow up. But as more radio telescopes came online with the capability to detect them in real time, the population of known fast radio bursts exploded. By 2021, the KIME telescope in Canada had detected more than 500 in just its first year of operation. Today, thousands of fast radio bursts from hundreds of unique sources are catalogued. The current catalogue shows they occur at a rate of perhaps 9,000 per day across the entire sky, bright enough for our instruments to detect. Fast radio bursts are fascinating for multiple reasons. Their dispersion, the way different frequencies arrive at slightly different times due to interaction with ionized plasma along the signal's journey, tells us about the invisible matter between galaxies. Their incredible brightness suggests compact energetic sources. Some fast radio bursts repeat, flashing again and again from the same spot in the sky, while others are never seen more than once. One fast radio burst, detected in 2020, came from a magnetar right here in our own galaxy during an X-ray outburst, providing strong evidence that at least some fast radio bursts originate from these highly magnetic neutron stars. But do all fast radio bursts come from magnetars? Are some from other sources? Could any be artificial? These questions remain open. The key distinction between fast radio bursts and traditional SETI signals is this: fast radio bursts are broadband and incredibly energetic. They're not the narrow, relatively low power transmissions you'd expect from a civilization trying to communicate across interstellar distances. If fast radio bursts are artificial, they'd represent technology capable of concentrating absurd amounts of energy into millisecond pulses, perhaps the kind of thing you'd use for propulsion rather than communication. Astronomer Avi Loeb has speculated they could be leakage from beamed energy systems used to push light sails, though this remains highly speculative. Most astronomers think natural explanations involving magnetars or other extreme astrophysical phenomena are more likely. There's also optical SETI, searching for laser pulses from space. The advantage of lasers is that they can be incredibly bright for brief moments, potentially outshining their host star in a narrow wavelength range. If an advanced civilization wanted to grab attention, pulsing a powerful laser would be one way to do it. Optical SETI looks for these brief flashes, often examining spectra taken during planet-hunting observations to see if there are unexplained bright lines that could represent laser light. Several optical SETI programs are now operating, including at the Lick Observatory's Automated Planet Finder and various other facilities. Veteran NASA scientist Richard Stanton recently reported detecting 2 fast identical pulses from a sun-like star about 100 light-years away that match similar pulses observed from a different star 4 years earlier. These pulses lasted only a fraction of a second and made the stars appear to briefly brighten and then fade in a pattern unlike natural stellar variability or atmospheric effects. They remain unexplained. Are they artificial, natural, but not yet understood? Instrumental artifacts? The investigation continues. This uncertainty is typical. Most signals of interest exist in a gray area where they're strange enough to be noteworthy, but not strange enough or repeatable enough to draw firm conclusions. So when we talk about the thousands of signals we've received and ignored, we're talking about this entire spectrum of detections. Narrowband candidates flagged by SETI searches, fast radio bursts catalogued by projects like CHIME and the Australian Square Kilometre Array Pathfinder, optical transients captured in spectroscopic surveys. Each one represents data, a moment when our instruments detected something, a question mark in the electromagnetic spectrum. Most get filtered out as interference or explained as natural phenomena, but some remain enigmatic, added to the growing list of things we don't quite understand. Certain signals stand out in the history of SETI, not because they've been confirmed as artificial, but because they've never been satisfactorily explained away and remain tantalizing possibilities. These are the ones that keep SETI scientists up at night, the famous cases that everyone in the field knows about. The most famous is the WOW signal, detected on August 15, 1977 by the Big Ear Radio Telescope at Ohio State University. Jerry Eman, a volunteer working on the SETI project, was analyzing computer printouts of radio data when he noticed something remarkable. The printout showed a series of alphanumeric characters representing signal intensity 6EQUJ5. This wasn't a message encoded in the signal, it was simply how the particular measurement system they were using represented the dramatic increase in signal strength. The signal lasted the full 72 seconds that Big Ear could observe any given point as Earth's rotation carried it through the telescope's field of view. It was strong, narrowband, and at 1420 MHz, right in the so-called waterhole where SETI researchers expected an artificial signal might appear. Eman circled the sequence on the printout and wrote "WOW" in the margin, giving the signal its enduring name. The signal appeared to come from the direction of the constellation Sagittarius. But here's the problem. It never repeated. Despite numerous attempts to detect it again using more sensitive instruments, including observations with the Very Large Array, nobody has ever seen the WOW signal return. In 2017, astronomer Antonio Paris proposed that the signal could have been caused by a hydrogen cloud surrounding comets that were passing through the region at the time, but this explanation was dismissed by other astronomers as inconsistent with the signal's properties. In 2024, researchers suggested it might have been a rare astrophysical event involving a hydrogen cloud suddenly brightening when energized by stellar emissions. The WOW signal embodies the central frustration of SETI, a signal that, at the time of detection, looked exactly like what you'd hope to find. Strong, narrowband, at a logical frequency, from a specific direction in space, and yet appearing only once, impossible to verify, remaining forever ambiguous. The lack of repetition doesn't necessarily mean it wasn't artificial. Perfect alignment between a transmitter on a rotating, orbiting planet and a receiver on another rotating, orbiting planet billions of kilometers away might indeed be a temporary circumstance that never quite repeats. But without confirmation, without additional detections, all we have is an intriguing anomaly from 1977. Then there's SHG B022+14A, a signal detected 3 times by SETI home volunteers using data from the Arecibo telescope in Puerto Rico. The detections occurred in 2003 and were reported in 2004. The signal appeared at about 1420 MHz with a rapid frequency drift, changing by 8 to 37 Hz per second. Each time it was detected, it was again at about 1420 MHz before the drift began, suggesting the source was resetting to the same base frequency. The signal came from a region between the constellations Pisces and Aries, where no stars are observed within 1,000 light-years of Earth, which was puzzling. If the frequency drift was caused by Doppler shift from a rotating planet, the planet would need to be spinning nearly 40 times faster than Earth. SETI Home officially stated this was not considered a likely extraterrestrial intelligence signal, noting it could be random noise, cosmic interference, or a technical glitch. But like the WOW signal, it was never definitively explained. More recently, we have BLC-1, Breakthrough Listen Candidate 1, detected in April and May 2019 by the Parkes telescope in Australia while observing Proxima Centauri, the closest star to our Sun. The signal was a narrowband emission at 982.00 MHz with a frequency drift consistent with motion from a planetary source. It appeared only when the telescope pointed at Proxima Centauri and seemed to disappear when pointed elsewhere. Proxima Centauri is known to have at least 2 planets, one of which orbits in the habitable zone. The discovery generated enormous excitement. This was potentially the first truly compelling SETI candidate in decades, but the excitement was tempered as analysis continued. Breakthrough Listen researcher Sophia Sheikh led a detailed investigation that examined a larger dataset of observations. She found around 60 other signals that shared many characteristics with BLC-1 but also appeared in off-source observations, meaning they were detected even when the telescope wasn't pointing, at Proxima Centauri. These signals showed regular frequency spacing corresponding to common oscillator frequencies used in electronic devices. The analysis strongly suggested BLC-1 was terrestrial radio frequency interference, probably from nearby human technology that just happened to coincide with the Proxima Centauri observations. The specific source was never identified, which is common. We live in an ocean of radio interference. Satellites, planes, electronic equipment, vehicles, all of them generate radio noise. Sometimes that interference sneaks through filters designed to eliminate it. Sophia Sheikh's careful work ruling out BLC-1 highlights a crucial point. SETI scientists want to find a signal. That's the entire goal. But they also understand that an incorrect positive detection would be scientifically disastrous. Claims of alien contact that later prove false damage credibility and waste resources. So the verification process is rigorous, sometimes frustratingly so. Candidates are analyzed from every angle. Possible terrestrial sources are exhaustively investigated. The default assumption is that any signal, no matter how interesting, is probably interference or a natural phenomenon until proven otherwise. This conservative approach is scientifically sound, but it means many intriguing signals get dismissed, added to the pile of things we can't quite explain but also can't confirm. The challenge is compounded by the transient nature of many signals. BLC-1 hasn't been detected again despite follow-up observations. The WOW signal remains unique. Even when signals do repeat, like some fast radio bursts, they don't follow predictable patterns that allow easy follow-up. FRB-12E1-NON-2, the first repeating fast radio burst discovered, emits bursts seemingly at random, sometimes going quiet for months, before erupting in clusters of activity. Trying to catch one of its bursts requires patience and dedicated telescope time. And telescope time is expensive, a precious resource that observatories carefully allocate among competing demands. This is why most signals end up being ignored, in the sense that they're flagged, analyzed, found to be ambiguous or inconsistent with extraterrestrial technology, and then set aside while the search continues. The archive of candidate signals grows. The list of things we don't fully understand lengthens. But without clear, repeatable, unambiguous detection, without the kind of evidence that would satisfy the rigorous standards of peer review, they remain footnotes rather than discoveries. When Breakthrough Listen launched in 2015, it represented a quantum leap forward for SETI. The numbers tell the story. $100 million over 10 years. Access to the Green Bank Telescope in West Virginia for 20% of its time. Access to the Parkes Telescope in Australia for 25% of its time. Collaborations with the Meerkat Array in South Africa, the Automated Planet Finder at Lick Observatory, and numerous other facilities. A plan to survey 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies. Open data available to anyone who wanted to analyze it. This wasn't a scattered collection of sporadic observations. This was systematic, comprehensive, and properly funded. The data started flowing immediately. In 2019, Breakthrough Listen released results from its first 3 years of radio observations, covering 1,702 nearby stars within about 160 light-years of Earth using the Green Bank Telescope and the Parkes Telescope. The search pipeline scanned through billions of radio channels, looking for narrowband signals that showed frequency drift. The vast majority of detected signals were immediately identified as terrestrial radio frequency interference. 2 filtering techniques reduced the haystack from tens of millions of signals down to a handful of candidates. These final candidates were carefully examined and determined to be unusual examples of human-generated interference that survived the filters. No extraterrestrial technosignatures were found, but the analysis placed the most stringent limits to date on the prevalence of radio-transmitting civilizations in our galactic neighborhood. The data release was also historic, representing petabytes of observations made publicly available, the largest SETI data release in history. Anyone with the skills and interest could download the data and conduct their own analysis, looking for signal types the official pipeline might have missed. And that's exactly what happened. In 2021, Peter Ma, then an undergraduate at the University of Toronto, applied machine learning techniques to 480 hours of Breakthrough Listen data from observations of 820 nearby stars. This dataset had previously been analyzed in 2017 using classical techniques and labeled as devoid of interesting signals. But Ma's new deep learning algorithm, which he had begun developing as a high school project, took a different approach. Instead of looking for signals that matched simulated templates, it used a semi-supervised technique combining autoencoders and random forests to identify anomalies, anything that looked weird compared to the background, even if it didn't match expectations. The algorithm returned 30,000 initial results. Ma and his colleague Leo Risk spent weeks manually inspecting each one. Many were obviously false positives, but some were strange, really strange. 8 signals passed all their tests. These signals were narrowband, just a few hertz wide. They showed non-zero drift rates, indicating relative acceleration between source and receiver. They appeared in on-source observations and not in off-source observations, suggesting they came from specific target stars rather than being local interference. They looked in many ways like ideal SETI candidates. The discovery was exciting, but also puzzling. These signals had all different drift rates and came from different stars. Classical algorithms had completely missed them. When the team showed the results to other Breakthrough Listen scientists, everyone was scratching their heads. These were compelling detections by any measure. Some astronomers called them more interesting than the wow signal. But there was a problem. When the team conducted follow-up observations of the stars where these 8 signals appeared to originate, they couldn't detect the signals again. Not once. The signals had vanished. This disappearing act doesn't necessarily mean the signals weren't real or weren't extraterrestrial. As discussed earlier, perfect alignment for detection might be a rare circumstance. If a civilization on a planet around one of these stars was transmitting a tightly focused beam, and Earth just happened to be in that beam's path for a brief window, we might detect it once and never again. Alternatively, if these were sporadic transmissions rather than continuous beacons, we might simply have missed the repeat. But the lack of repetition means the signals remain unconfirmed, added to the growing list of intriguing but ambiguous detections. The power of Ma's machine learning approach was that it found signals classical methods missed. This raises an important question. How many other interesting signals are hiding in the archival data, waiting for new techniques to uncover them? The answer is probably quite a few. As machine learning and artificial intelligence continue to advance, we're getting better at sifting through massive datasets to find subtle patterns. The challenge is distinguishing genuine anomalies from the weird edge cases of terrestrial interference, the one-in-a-million coincidences that look interesting but ultimately are just noise. Another major breakthrough LISTEN survey examined the centers of 97 nearby galaxies. This was a different kind of SETI search. Instead of looking for relatively low-power transmissions from individual stars, this survey looked for extremely powerful signals that could be detected across intergalactic distances. The reasoning was that if super-advanced civilizations exist, ones capable of harnessing the energy of entire stars or galaxies, they might produce detectable electromagnetic signatures visible from millions of light-years away. These would be Kardashev Type 2 or Type 3 civilizations, existing on scales of technological capability utterly beyond our current reach. The survey covered 4 frequency bands totaling more than 10 gigahertz of bandwidth. It observed 97 galaxies representing all major morphological types: spirals, ellipticals, dwarf spheroidals, irregulars. The observations generated 1,519 candidate signals that were not immediately attributable to radio frequency interference. After algorithmic processing, correlation with known interference populations, and extensive visual inspection, the team found no compelling evidence of technosignatures. But, like all breakthrough LISTEN work, the data are public, available for anyone to reanalyze with new methods. The COSMIC project, operating at the Carl G. Jansky Very Large Array in New Mexico, took yet another approach. Rather than conducting dedicated SETI observations, COSMIC piggybacks on the VLA Sky Survey, which is conducting a comprehensive survey of the entire visible sky at radio wavelengths. COSMIC receives a copy of the raw data in real time before any standard processing, allowing it to search for transient signals that might be missed by conventional astronomical analysis. This commensal approach, searching for technosignatures in data collected for other purposes, dramatically increases the amount of sky coverage without requiring dedicated telescope time. Over its operations through 2024, COSMIC examined more than 950 million objects across the sky, looking for narrow-band signals with the characteristic Doppler drift expected from a transmitter in motion. Like other searches, it found no compelling technosignature candidates, but it demonstrated the power of automated, real-time analysis operating at scale. These systems can flag interesting signals as they're detected, enabling rapid follow-up observations before the source moves or the signal changes. In the future, networks of telescopes operating with coordinated real-time processing could provide the redundancy needed to immediately confirm or rule out candidate signals. The takeaway from all these breakthrough LISTEN results is twofold. First, we're searching more sky with greater sensitivity across more frequency ranges than ever before in history. The coverage is staggering compared to the early days of SETI. Frank Drake listened to 2 stars for 150 hours total. Breakthrough. LISTEN has observed thousands of stars for thousands of hours, scanned huge swaths of the galactic plane, examined nearby galaxies, and made all the data public. Second, despite this enormous effort, we haven't found a confirmed technosignature. That null result is itself scientifically valuable, placing constraints on how common detectable alien civilizations might be. But it also emphasizes how hard this search is and why most signals end up being classified as interference or natural phenomena. While SETI searches focus on potential artificial signals, the field of fast radio burst astronomy has exploded quite literally over the past decade and a half. These aren't your grandmother's radio signals. They're powerful, brief, mysterious, and they're rewriting our understanding of the radio universe. When Duncan Lorimer discovered the first fast radio burst in 2007, hiding in archival data from 2001, it was so unusual that many astronomers were skeptical it was real. A 5-millisecond burst of radio energy from billions of light-years away, releasing as much energy as the sun puts out in nearly a century? It sounded absurd. But as more were discovered, the reality set in. These things are real, they're numerous, and they're genuinely bizarre. The breakthrough came with CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a specialized radio telescope designed to map neutral hydrogen across vast swaths of the sky. CHIME looks like 4 enormous half-pipes lying on the ground, 100 meters long by 20 meters wide each, covered in radio antennas. It can't move, but it doesn't need to. As Earth rotates, CHIME's field of view sweeps across the sky, and digital signal processing allows it to simultaneously monitor thousands of different directions. This design makes CHIME incredibly effective at detecting fast transient events like fast radio bursts. Between 2018 and 2019, CHIME's first year of operations, it detected 535 new fast radio bursts. That's more than quintupling the known population in a single year. Before CHIME, there were less than 100 total catalogued fast radio bursts. CHIME showed they're common, occurring at an estimated rate of about 800 bright enough to detect per day across the entire sky, possibly as many as 9,000 if you count fainter ones. If your eyes could see radio flashes, you'd see them constantly, flaring across the heavens like cosmic fireworks. The CHIME catalog revealed important patterns. Most fast radio bursts are one-off events, never repeating from the same location. But some do repeat. The CHIME data showed 61 repeating bursts from 18 different sources. These repeaters look different from the one-offs. Their bursts last slightly longer and cover more focused frequency ranges. This strongly suggests there are at least 2 distinct populations of fast radio bursts, possibly arising from different astrophysical mechanisms. FRB 121102 was the first repeater discovered, initially detected in 2012 and observed bursting repeatedly ever since. It's located in a dwarf galaxy about 3 billion light-years away. In September 2018, a neural network analyzing CHIME data found 72 bursts from FRB 121102 spanning just 5 hours. The source exhibits periodicity, active for about 90 days followed by 67 days of silence, suggesting the bursts might be associated with orbital motion in a binary system, perhaps a neutron star orbiting a massive star or black hole. But even this periodicity isn't perfect, and the bursts within active windows seem to occur randomly. More recently, FRB 2020-40619d was observed by the Meerkat telescope in South Africa. Over the course of just a few days, it produced 249 bursts, making it one of the most active repeaters ever observed. The source is located in a dwarf galaxy about 700 million light-years away. Among these 249 bursts, astronomers noticed something fascinating. The bursts varied wildly in their properties. Some lasted mere milliseconds, while others stretched for tens of milliseconds. Their frequencies ranged across a broad spectrum. This diversity suggests FRB 2020-40619d isn't just firing off identical copies of the same signal. Whatever process creates these bursts has complex dynamics, possibly involving changes in the source environment or emission mechanism between bursts. Then there's the magnetar connection, the smoking gun that finally linked at least some fast radio bursts to a known astrophysical object. On April 28, 2020, multiple telescopes around the world detected something unprecedented. The CHIME telescope in Canada and the STARE-2 array at Caltech both picked up a powerful millisecond duration radio burst. This burst, designated FRB 2004-28, was exceptional for several reasons. It came from within our own Milky Way galaxy, only about 30,000 light-years away in the constellation Vulpecula. It came from the direction of SGR 1935+215b4, a known magnetar that had been undergoing a period of intense X-ray activity. And, crucially, the radio burst occurred simultaneously with an X-ray burst from the same source, observed by the Integral spacecraft and other X-ray telescopes. This was the connection astronomers had been hoping for. Magnetars are neutron stars with magnetic fields more than a quadrillion times stronger than Earth's magnetic field, among the most powerful magnetic fields known to exist in the universe. These ultra-strong fields decay over time, powering spectacular X-ray flares and other high-energy phenomena. Theoretical models had suggested magnetars could produce fast radio bursts through mechanisms involving magnetic explosions or relativistic shock waves in the magnetar's surrounding plasma. FRB 2004-228 provided direct observational evidence supporting this hypothesis. The energy released in FRB 2004-228 was about 4,000 times greater than any radio burst previously detected from the Crab pulsar, which had been the brightest source of galactic radio bursts known. It was only about 30 to 40 times less energetic than the weakest extragalactic fast radio bursts detected, suggesting it belonged to the same population despite being much closer. If this burst had originated from a distant galaxy like other fast radio bursts, at a distance of 500 million light-years or more, it would have appeared far too faint for current instruments to detect. This raises an intriguing question. How many fast radio bursts are we missing simply because they're intrinsically less energetic and only visible when they occur relatively nearby? Follow-up observations of SGR 1935+2-215 have continued to reveal surprises. In the months after FRB 2004-228, astronomers detected additional radio bursts from the same magnetar, though these were much weaker and didn't coincide with X-ray flares. The magnetar also entered a radio pulsar phase, emitting regular pulses like a typical pulsar, but with characteristics suggesting the pulses and bursts originate from different regions of the magnetar's magnetosphere. This complexity indicates that even within a single source, multiple emission mechanisms might be at work. But while FRB 2004-228 established that magnetars can produce fast radio bursts, it didn't solve the entire mystery. The burst from SGR 1935+2154 was significantly less energetic than most extragalactic fast radio bursts. Does this mean there are different classes of magnetars, with hyperactive ones in distant galaxies producing the extremely luminous bursts we typically detect? Or are there additional factors, perhaps related to the surrounding environment or viewing geometry, that boost the observed brightness? Scientists have proposed models involving two populations of magnetars, ordinary ones like SGR 1935+21504, and much rarer, hyperactive ones, perhaps associated with recent supernova explosions or neutron star mergers. The repeating fast radio burst FRB 12102 exhibits behavior that might support the hyperactive magnetar hypothesis. This source flares dramatically, sometimes producing dozens of bursts in a single hour, then goes silent for weeks or months. During active periods, the bursts span a wide range of frequencies and show rapid frequency evolution within individual bursts. One interpretation is that FRB 12102 is powered by a young magnetar, perhaps only a few hundred years old, still in an extremely energetic phase of its evolution. As the magnetar ages and its magnetic field gradually decays, the burst activity should diminish, eventually ceasing altogether. Other fast radio burst models don't involve magnetars at all. Some theories propose that one-off, non-repeating fast radio bursts could arise from cataclysmic events like mergers of compact objects, two neutron stars colliding, or a neutron star falling into a black hole. These violent events would produce intense bursts of radio emission as a one-time occurrence, never to repeat because the source is destroyed in the process. The challenge with catastrophic models is that fast radio bursts occur very frequently, thousands per day across the sky, which would require an implausibly high rate of such mergers. Magnetar models better explain the observed rates, especially with repeaters demonstrating that at least some sources survive to burst again. Then there are exotic possibilities. In 2017, Harvard astronomer Avi Loeb and colleague Manasvi Lingam proposed that fast radio bursts could be leakage from powerful beamed energy systems used by advanced civilizations to propel spacecraft across interstellar distances. The idea is that a civilization might use enormous transmitters to push light sails, thin reflective sheets that accelerate when hit by radiation. If a beam powerful enough to push a spacecraft happens to sweep across Earth as the sail moves, we detect it as a fast radio burst. The repeating nature of some fast radio bursts would correspond to the regular use of these propulsion systems, while one-off bursts might be initial acceleration phases or deliberate beacons. This hypothesis is highly speculative, and most astronomers consider natural explanations far more likely, but it's not scientifically invalid. The hypothesis makes testable predictions such as correlations between burst properties and the presence of planetary systems or geometric patterns in repeater activity that would suggest engineered beaming. So far, no such patterns have been found. Occam's razor suggests we shouldn't invoke advanced civilizations when astrophysical phenomena adequately explain observations. Still, the possibility that at least some fast radio bursts could be artificial technosignatures remains an active area of discussion, particularly for repeaters with unusual properties that don't quite fit natural models. What's clear is that fast radio bursts have opened an entirely new window into the violent, high-energy universe. They're teaching us about magnetars, neutron star evolution, intergalactic plasma, and the physics of extreme magnetic fields. Whether any of them are artificial remains an open question, but even if they're all natural, they represent one of the most exciting areas of current astrophysical research. With thousands of signals detected, why do we ignore the vast majority? The answer reveals the profound challenge of distinguishing potential alien transmissions from the overwhelming background of terrestrial and natural sources. Radio frequency interference is the biggest culprit. Earth is bathed in artificial radio emissions. Every cell phone, every satellite, every radar installation, every electronic device that generates radio waves contributes to the electromagnetic smog we live in. From the perspective of a radio telescope, Earth is unbelievably bright, far brighter than most cosmic sources. It's like trying to see the faint stars while someone's shining a billion flashlights in your face. Modern SETI searchers must contend with an environment utterly saturated with radio noise. The genius of traditional SETI methodology is using on-source and off-source observations to filter out terrestrial interference. Point your telescope at a target star. Listen. Then point away from the star and listen again. Any signal that appears in both observations is obviously terrestrial, arriving from Earth or a satellite, not from the target. Only signals that appear when pointing at the target and disappear when pointing away are interesting. This seems straightforward, but complications abound. Satellites don't stay in one place. They move across the sky. A satellite passing through your telescope's field of view while you're observing a target star will appear to come from that star's direction. Its signal will show up in the on-source observation and vanish in the off-source observation, perfectly mimicking an extraterrestrial source. Sophisticated algorithms try to identify and filter out satellite signals based on their characteristic patterns, but sometimes they slip through, especially if the satellite is untracked or transmitting in unexpected ways. Ground-based sources are equally problematic. Vehicles driving past the telescope, aircraft flying overhead, a technician's cell phone inadvertently left on near-sensitive electronics, remote rural communities tens of kilometers away whose radio emissions normally don't reach the telescope but occasionally propagate through atmospheric conditions. All of these create spurious signals that must be identified and eliminated. The Green Bank Telescope operates in the National Radio Quiet Zone, a region where radio transmissions are heavily restricted to protect the telescope from interference, yet even there, contamination is a constant battle. Some radio frequency interference is subtle. Modern electronics use clocks and oscillators that generate radio harmonics at specific frequencies. These harmonics can show up in telescope data as narrowband signals, sometimes with frequency drifts that mimic celestial sources. The BLC-1 signal from Proxima Centauri, discussed earlier, was ultimately attributed to this kind of interference. The signal's frequency, when carefully analyzed, matched oscillator frequencies commonly used in electronics. The fact that similar signals appeared in off-source observations, though initially missed in preliminary analysis, sealed the case. BLC-1 was almost certainly terrestrial. The verification process for SETI candidates is deliberately rigorous. When a signal of interest is flagged, multiple follow-up steps are taken. First, examine all the data carefully to see if similar signals appear elsewhere in the observation run, particularly in off-source pointings. Second, re-observe the target to see if the signal repeats. Third, have independent observatories observe the same target to see if they detect anything. Fourth, analyze the signal's properties in detail: its bandwidth, drift rate, whether it appears at frequencies that match known human technology, whether it shows polarization or modulation patterns that provide clues to its origin. Most candidates fail one or more of these tests. The signal doesn't repeat in follow-up observations, suggesting it was transient interference rather than a continuous transmission. Or it does show up in off-source observations when examined more carefully, revealing it as terrestrial. Or it has characteristics that match known sources of radio frequency interference. The 8 signals discovered by Peter Ma's machine learning algorithm, for example, remain unconfirmed because they never repeated despite extensive follow-up observations of the stars where they apparently originated. Even when signals pass initial filters, ambiguity often remains. The WOW signal passed every test available in 1977. It appeared once, strongly, in the on-source observation of a specific region of sky. It had the right bandwidth, the right frequency, the right duration, but it never repeated despite dozens of subsequent observations of the same region. Without repetition, verification is impossible. Is it an artificial transmission we happen to catch during one fleeting moment of perfect alignment? Is it an extremely rare natural phenomenon we don't understand? Is it terrestrial? Interference that coincidentally appeared exactly when the telescope was pointed at that part of the sky and never occurred again? We don't know. We may never know. Fast radio bursts face similar challenges. Most don't repeat. We detect them once and never again. This makes detailed study difficult. We can't point multiple telescopes at the source because we don't know when the next burst will arrive. We can't test theories about their behavior because we have only a single data point. The repeaters are incredibly valuable precisely because they allow follow-up. We can watch them, catalog their bursts, study how their properties change over time, compare simultaneous observations from multiple instruments. But even with repeaters, patterns are often irregular and unpredictable, frustrating attempts to develop comprehensive models. Natural astrophysical sources also produce signals that can look suspicious in initial detection. Pulsars emit regular radio pulses that could be mistaken for artificial beacons if you don't recognize them as pulsars. Quasars and active galactic nuclei produce intense radio emission across broad frequency ranges. Stellar flares can create bursts of radio energy. Marsers in star-forming regions produce narrowband radio emission. All of these natural sources have characteristic properties that distinguish them from artificial signals once properly analyzed, but in raw data, they can trigger detection algorithms designed to flag anything unusual. The challenge is exacerbated by the sheer volume of data modern SETI projects generate. Breakthrough. Listen alone creates tens of terabytes of data every week. Analyzing all of this data for all possible signal types is computationally intensive. Algorithms must be carefully tuned to balance sensitivity against the rate of false positives. Too conservative, and you might miss real signals. Too liberal, and you're drowning in false alarms, wasting valuable time and resources investigating interference. This is why machine learning and artificial intelligence are becoming essential tools. Traditional detection algorithms look for signals matching specific templates: narrowband emissions with certain drift rates, pulses with certain characteristics. But these algorithms miss signals that don't fit their templates. Machine learning approaches can identify anomalies, anything that looks different from the background, without requiring exact matches to predetermined patterns. The trade-off is that machine learning generates many more candidates, most of which turn out to be weird interference or instrumental artifacts rather than genuine detections. But by finding signals that classical methods miss, Like the 8 candidates Peter Ma discovered, machine learning expands the search space. Another factor in why most signals are ignored is resource limitation. Telescope time is expensive and heavily oversubscribed. For every hour spent doing SETI observations, some other scientific project doesn't get observing time. Follow-up observations of candidates compete with other priorities: mapping galaxies, studying exoplanet atmospheres, observing supernovae, monitoring pulsars. Every candidate that warrants follow-up requires a cost-benefit analysis. How compelling is this signal? How likely is it to be real versus interference? How much telescope time would be needed to adequately investigate it? Given finite resources, only the most promising candidates receive extensive follow-up. Sometimes signals are ignored simply because they're not interesting enough to pursue intensively. A signal that appears once, doesn't repeat, and has properties consistent with known interference might get noted in a catalog but not investigated further. There are thousands of such signals in SETI databases. They're not definitively explained, but neither do they rise to the level of demanding immediate, extensive investigation. They exist in a gray zone, potentially interesting, probably mundane, unlikely to be resolved without significant resource investment that might be better spent elsewhere. This reality frustrates some people. There's a perception that SETI scientists are too quick to dismiss candidates, too conservative in their standards, missing genuine signals because they're unwilling to seriously pursue intriguing detections. But this perception misunderstands the scientific process. The standard of proof for claiming detection of extraterrestrial intelligence is and should be extraordinarily high. An incorrect positive would be one of the most consequential scientific errors possible. It would misinform our understanding of the universe, waste resources on follow-up of a false lead, and damage public trust in science. SETI researchers understand this. They want to find a signal, but they want to be right about it. That requires caution, rigor, and the willingness to set aside candidates that don't meet the burden of proof, no matter how much you might wish otherwise. The integration of artificial intelligence and machine learning into SETI represents a fundamental shift in how we search for extraterrestrial intelligence. For decades, SETI relied on classical detection algorithms, match filters, drift search routines, pulse detection schemes. These methods work well when you know exactly what you're looking for, but they struggle with unexpected signal types or subtle patterns buried in noise. Enter artificial intelligence. Machine learning algorithms can be trained to recognize patterns without being explicitly programmed with rules for what those patterns look like. This makes them extraordinarily powerful for data-rich domains where the signal of interest might not match your preconceptions. Peter Ma's discovery of 8 new SETI candidates using a deep learning algorithm exemplifies this potential. Ma developed his approach while still in high school, then refined it as an undergraduate at the University of Toronto. His algorithm combined 2 machine learning techniques, autoencoders and random forests. Autoencoders are neural networks trained to compress data into a lower dimensional representation and then reconstruct the original data from that compressed form. The clever part is that the compression forces the algorithm to learn what's essential about the data, filtering out noise and irrelevant details. Random forests are ensemble methods that combine many decision trees to classify data, robust against overfitting and effective at capturing complex relationships. Ma trained his algorithm on data that had already been analyzed by classical methods and labeled as not containing interesting signals. This is semi-supervised learning. The algorithm learns to identify what normal looks like and then flags anything that deviates from normal. When applied to 480 hours of breakthrough listen observations covering 820 nearby stars, the algorithm returned 30,000 initial hits. This demonstrates both the power and the challenge of machine learning. It found far more candidates than classical methods, but the vast majority were false positives that had to be manually inspected and rejected. Ma and his colleague Leo Risk spent weeks reviewing the 30,000 candidates. They looked for signals with properties that made them compelling: narrowband emission, non-zero drift rates, appearing in on-source observations but not off-source. After this painstaking process, 8 signals survived all their filters. These signals had properties consistent with artificial transmissions, narrow bandwidths, frequency drifts suggesting relative motion between source and receiver, spatial association with specific target stars. Classical algorithms had completely missed them, possibly because their exact characteristics didn't match the template search parameters. The discovery was exciting, but also humbling. When Breakthrough Listen conducted follow-up observations of the stars where these 8 signals appeared to originate, none of them were detected again. The signals had vanished. This is the recurring frustration of SETI. Intriguing detections that don't repeat, leaving you with a single data point and profound ambiguity about its nature. The lack of repetition doesn't invalidate the detections or the method. It means we don't have confirmation. The signals could be transient artificial transmissions we happen to catch during brief moments of perfect alignment. They could be rare natural phenomena. They could be unusual instances of terrestrial interference that slipped through despite the algorithm's efforts to filter such signals out. Without additional detections, we can't say. But the fact that machine learning found signals classical methods missed demonstrates its value. There may be many more such signals hiding in archival data, waiting for advanced algorithms to uncover them. Other research groups are applying artificial intelligence to various aspects of SETI and radio astronomy. Neural networks are being trained to identify radio frequency interference more effectively than classical approaches. Machine learning classifies transient radio sources, distinguishing pulsars from fast radio bursts from interference from unknown phenomena. Algorithms detect patterns in the properties of repeating fast radio bursts, looking for periodicity or correlations that might reveal their nature. Artificial intelligence also optimizes observing strategies, deciding which targets to observe and for how long based on real-time analysis of data, quality, and signal characteristics. One particularly exciting development is real-time signal processing using artificial intelligence. Traditional SETI searches record vast amounts of data, then analyze it offline, sometimes months or years after observation. By the time an interesting signal is identified, the opportunity for immediate follow-up has passed. Real-time systems like the COSMIC project at the Very Large Array analyze data as it's collected, flagging interesting signals within seconds or minutes of detection. This allows rapid repointing of telescopes to confirm or rule out candidates before circumstances change. The COSMIC system demonstrated this capability by processing data from the VLA Sky Survey, examining millions of sources for narrowband signals with Doppler drift. All processing happened in real time, with candidates immediately flagged for human review. While COSMIC found no confirmed technosignatures, it proved the concept of automated commensal SETI observations. Commensal meaning the SETI search piggybacks on observations conducted for other purposes, extracting signal processing copies of the data before conventional astronomical analysis destroys the information SETI needs. This dramatically expands survey coverage without requiring dedicated telescope time. Future SETI systems will integrate artificial intelligence even more deeply. Imagine networks of radio telescopes operating globally, all feeding data to centralized machine learning pipelines that analyze signals from every instrument in real time. When one telescope detects a candidate, the system automatically tasks other telescopes to observe the same source, providing immediate confirmation or rejection. Artificial intelligence manages this entire process, coordinating observations, analyzing data, and alerting human scientists only when candidates pass multiple levels of verification. Machine learning also enables searches for signal types humans might not think to look for. Traditional SETI focuses on narrowband continuous waves or simple pulses, the kinds of signals we'd use if we wanted to communicate across interstellar distances. But maybe alien civilizations use fundamentally different communication modalities, complex frequency-modulated signals, spread spectrum transmissions, exotic forms of modulation we haven't invented. Humans can't anticipate every possibility, but machine learning algorithms trained on the full, multidimensional space of signal characteristics might find patterns we'd never explicitly search for. There are challenges, of course. Machine learning algorithms are only as good as their training data. If trained predominantly on terrestrial signals, they might develop biases that cause them to reject artificial-looking extraterrestrial signals as too much like interference. If trained to be too sensitive, they generate overwhelming numbers of false positives. Tuning these algorithms requires careful validation and iteration. There's also the black box problem. Deep learning models sometimes make decisions based on subtle correlations in their training data that humans don't understand. When a neural network flags a signal as interesting, can we trust its judgment? How do we explain that judgment to others? Despite these challenges, the trajectory is clear. Artificial intelligence will become increasingly central to SETI as data volumes grow beyond human analytical capacity. The question isn't whether to use machine learning, but how to use it most effectively, combining its pattern recognition capabilities with human insight and scientific judgment to maximize our chances of detecting that one genuine signal among millions of false alarms. Confirmation is the central challenge that has prevented SETI from claiming success despite decades of searching and thousands of interesting signals detected. Without confirmation, without repeatable observations that multiple independent groups can verify, we don't have discovery. We have candidates, intriguing anomalies, things that warrant investigation, but not answers. Why is confirmation so difficult? Several factors conspire against us. First is the ephemeral nature of signals. Most SETI candidates appear once and never again. The WOW signal lasted 72 seconds in 1977 and hasn't been seen since despite numerous attempts to re-observe the same region of sky. The 8 signals found by Peter Ma's algorithm occurred during specific observations and vanished in follow-up. Even BLC-1, which appeared in multiple observation sessions, hasn't been detected since the initial discovery period in 2019. This disappearing act could have several explanations. One is that the signals are extremely rare events, bursts or transmissions that occur irregularly on timescales we haven't figured out. If an alien civilization transmits a beacon once every few years, and we happen to observe during one of those transmission periods, we might not see it again unless we observe at the right time. This is especially problematic for targeted searches where telescope time is limited. You might observe a star for a few hours, detect something, but not be able to obtain enough telescope time for prolonged monitoring to catch a repeat. Geometric alignment is another factor. Imagine an advanced civilization using a powerful directed energy beam to communicate or to propel spacecraft. Such a beam would be tightly focused, perhaps only a few degrees wide, concentrating energy for efficiency. If Earth happens to cross that beam's path, we'd detect it. But the beam is sweeping through space as the transmitting planet rotates and orbits, and our planet is also rotating and orbiting. The alignment that allowed detection might last only briefly, possibly just minutes, before our planet's motions carry us out of the beam. Re-establishing that alignment could require waiting for the precise configuration to recur, which might be years or decades or never within our observing windows. Fast radio bursts epitomize this challenge. Most are one-time events. We detect them with no advance warning, observe for a fraction of a second, and then they're gone forever. Even repeaters are unpredictable. FRB 12Y102 goes through active and quiet phases, but within active phases, bursts seem to occur randomly. You can dedicate telescope time to observing it, but you might watch for hours and see nothing, or you might catch a spectacular burst sequence. This unpredictability makes targeted follow-up difficult and resource-intensive. Terrestrial interference compounds the confirmation problem. When you detect a candidate signal, you can never be completely certain it wasn't interference that happened to coincide with your observation. Even if it passes all your filters, even if it appears only in on-source observations and has properties consistent with an extraterrestrial origin, there's always residual doubt. The only way to overcome that doubt is independent confirmation. Have another telescope at another location, observe the same source, and detect the same signal. Interference is local. A genuine extraterrestrial signal should be detectable by any sufficiently sensitive telescope pointing at the source. But this requires coordination. You detect a candidate, you alert other observatories, they point their telescopes at the source, and they see nothing. Does this mean your detection was interference? Or does it mean the signal was transient and you caught it during its brief appearance while others missed it? This ambiguity is maddening. Without simultaneous multi-telescope observations, you can't definitively distinguish between these scenarios. The SETI community has developed verification protocols to address this. When a strong candidate is detected, the International Academy of Astronautics SETI Permanent Committee has guidelines for responsible announcement and verification. The basic principle is, don't claim detection of extraterrestrial intelligence based on a single observation from a single telescope. Attempt immediate confirmation using independent instruments. If confirmation is obtained, expand observations to characterize the signal thoroughly before making any public announcement. If confirmation fails, continue investigations quietly while maintaining scientific rigor. These protocols exist because false positives in SETI are uniquely consequential. Claiming detection of alien intelligence is perhaps the single most significant scientific announcement possible. Getting it wrong would be catastrophic for the credibility of SETI research and for public trust in science generally. Everyone remembers the 1996 claim of fossilized life in Martian meteorite ALH84001, announced with great fanfare, only to be walked back as subsequent analysis showed the evidence was ambiguous at best. SETI researchers want to avoid a similar situation, but conservative verification standards mean many intriguing signals are never pursued to definitive conclusions. They're flagged, analyzed, found to be ambiguous, and then essentially shelved. The signal database grows, but without the telescope time and resources for extensive follow-up, most candidates remain unresolved. Scientists publish papers describing the signals and their properties, but conclusions are cautious. We detected an interesting signal. It has these characteristics. It doesn't match known sources of interference, but we also couldn't confirm it. Further observations are needed. And often, those further observations never happen because other priorities take precedence. Funding is part of the problem. SETI has historically been underfunded compared to other areas of astronomy. Breakthrough Listen's $100 million budget over 10 years is substantial, but still modest compared to major observatory projects. Most SETI researchers work on SETI part-time, with their primary appointments in conventional astronomy or physics. Telescope time is allocated through competitive processes where SETI proposals must compete with proposals for observations of black holes, exoplanets, cosmology, and myriad other topics. Securing time for follow-up of unconfirmed SETI candidates is challenging, especially when the candidates are ambiguous. The SETI community has discussed creating dedicated confirmation networks, arrays of smaller telescopes distributed globally, operated specifically for rapidly responding to candidate detections. If any primary telescope detects a signal, the network would immediately observe the same target from multiple locations, providing near real-time confirmation or rejection. Such a network doesn't yet exist, partly due to cost, partly due to the challenge of coordinating international collaborations, and partly because the perceived probability of detection is low enough that dedicating resources to confirmation infrastructure seems premature. Another approach is building confirmation capabilities into future telescope designs. The square-kilometer array, when complete, will have enormous sensitivity and the ability to form multiple independent beams observing different parts of the sky simultaneously. SETI observations could be conducted commensally, with some beams dedicated to SETI searches, while others do conventional astronomy. If a candidate is detected in one beam, other beams could immediately swing to observe the same target, providing instant confirmation or rejection. This kind of built-in redundancy could finally break the confirmation deadlock that has stymied SETI for so long. Until then, we're stuck in a frustrating limbo. We have thousands of signals, many of them intriguing, none of them confirmed. We know we're missing potential signals due to coverage gaps and sensitivity limits. We know we're probably detecting interference and calling it interesting. We know that somewhere in the data, there might be a genuine extraterrestrial transmission we haven't recognized, but we can't be sure. And without certainty, without confirmation, the search continues. Even without confirmed detections, the accumulation of null results and ambiguous signals tells us something about the universe and our place in it. Every star observed without detecting a technosignature places constraints on how common detectable civilizations are. Every fast radio burst characterized as natural limits the parameter space for artificial explanations. Absence of evidence is not evidence of absence, but it is evidence for updating our priors. The Drake equation provides a framework for thinking about this. Recall that it multiplies together factors like the star formation rate, fraction of stars with planets, number of habitable planets per system, fraction where life emerges, fraction developing intelligence, fraction developing detectable technology, and length of time civilizations remain detectable. The result is an estimate of the number of currently detectable civilizations in the galaxy. In 1961, Drake and his colleagues at the first SETI meeting estimated this number could range from thousands to millions, depending on how optimistic you were about each factor. The assumption was that if technological civilizations commonly arise and tend to be long-lived, the galaxy should be teeming with them, and we detect signals relatively easily. 60 years of searching without success forces us to reconsider those optimistic assumptions. Breakthrough. LISTEN's survey of 1,702 nearby stars within 160 light-years, with sensitivity to detect radar strength transmissions or stronger, found nothing. If even 1% of stars hosted civilizations broadcasting powerful radio signals, we'd expect to have detected about 17 signals in this sample. We detected 0. This allows us to place an upper limit. At most, a tiny fraction of nearby stars, probably less than 0.01% and potentially far less, are currently broadcasting detectable radio signals in our direction. Similar logic applies to the galaxy center searches. Breakthrough Listen observed 97 nearby galaxies looking for extremely powerful signals detectable across intergalactic distances. These would be Kardashev Type 3 civilizations, ones harnessing the energy of billions of stars. The survey was sensitive to transmissions with power outputs of 10-30 watts or more, unimaginably vast by human standards, but theoretically possible for sufficiently advanced civilizations. 0 such signals were detected, suggesting that super civilizations, if they exist, don't engage in galaxy-spanning radio broadcasting, at least not in ways we'd recognize. This doesn't mean civilizations don't exist. It means they're either rare, or they don't broadcast in ways we can detect, or they're short-lived, or some combination of these factors. Each scenario has implications. If civilizations are rare, perhaps the emergence of intelligent, technological life is an extremely low probability event, occurring only on a tiny fraction of habitable planets. This is the rare Earth hypothesis. While microbial life might be common, the sequence of events required to produce intelligent, communicative species is so improbable that we might be alone in the galaxy or even the observable universe. Alternatively, civilizations might be common but quiet. Maybe radio communication is a brief phase in technological development, used for only a century or two before civilizations switch to more efficient methods we can't detect. Fiber optics, neutrino beams, quantum entanglement communication, or technologies we haven't imagined. If every civilization goes through a radio window lasting a few centuries, and stars are billions of years old, the odds of us and another civilization being in our respective radio windows simultaneously and close enough to detect each other are very small. Or maybe civilizations are common but short-lived. Perhaps every technological civilization encounters catastrophic risks: nuclear war, environmental collapse, runaway artificial intelligence, bioengineered pandemics. If civilizations typically destroy themselves within centuries or millennia of developing radio technology, there would never be many detectable civilizations existing at once. We might be the only one in our galaxy right now, even if thousands or millions have existed in the past and thousands will exist in the future. The Fermi paradox encapsulates this puzzle: the apparent contradiction between high estimates for the probability of extraterrestrial civilizations and the complete lack of evidence for them. Enrico Fermi famously asked, "Where is everybody?" If civilizations are common, shouldn't we see evidence of their existence? Shouldn't we detect their signals, observe their megastructures, find traces of their visits to our solar system? The silence is deafening and demands explanation. Many resolutions to the Fermi paradox have been proposed. Some invoke observational selection effects. We're looking in the wrong places, at the wrong frequencies, for the wrong kinds of signals. Some suggest civilizations deliberately hide, avoiding detection for reasons related to security or cosmic sociology. Some propose that interstellar travel is far harder than we imagine, preventing civilizations from physically expanding across the galaxy. Some argue that intelligence and technology don't necessarily go together, that there might be many intelligent species that never develop radio transmitters or space travel. SETI data is starting to constrain these possibilities. If civilizations are common and long-lived, and they broadcast over a wide range of frequencies, we should have detected them by now given the sensitivity and sky coverage of modern searches. We haven't, which suggests at least one assumption in that chain is wrong. Either civilizations are rarer than optimists thought, or they don't broadcast promiscuously, or they're shorter-lived than hoped. None of these conclusions is definitive because our searches are still incomplete, but the lack of detections is informative. Fast radio bursts contribute their own statistical story. Thousands of these events occur daily across the observable universe. If even a small fraction were artificial, we'd expect to see patterns or characteristics that don't match natural explanations. We haven't. Every fast radio burst property discovered so far is consistent with natural astrophysical sources, primarily magnetars. The fact that we can explain fast radio bursts without invoking technology suggests Occam's razor favors natural explanations. This doesn't prove none are artificial, but it reduces the probability that we're constantly observing alien megastructures or propulsion systems without recognizing them. The optical CT observations add another data point. Despite surveys examining thousands of stars for laser pulses, no confirmed artificial optical signals have been detected. This narrows the possibility space further. If civilizations exist and want to communicate, they're not using the methods we've searched for most thoroughly: narrowband radio, powerful radio beacons, or optical laser pulses. Either they use other methods, or they're not trying to communicate, or they're not there. Bayesian reasoning allows us to update our beliefs based on evidence. Before SETI began, without any data, someone might reasonably assign a wide probability distribution to the prevalence of detectable civilizations. Maybe 1 in 100 stars, maybe 1 in a million, maybe 1 in a trillion. As searches accumulate without positive results, we update toward lower probabilities. We can calculate how much to update using the sensitivity and coverage of the searches. Every star observed without detection shifts the probability distribution slightly toward civilizations are rarer than we thought. After thousands of stars and still no detection, the shift is substantial. However, we must be careful not to overinterpret null results. Absence of detection could mean absence of civilizations, or it could mean our detection methods are inadequate. If civilizations communicate primarily through fiber optic cables or highly directional lasers not aimed at us, we wouldn't detect them no matter how many stars we observe. If they use radio bands we're not monitoring, or modulation schemes we're not searching for, or communication methods based on physics we don't understand, they'd be invisible to current searches. SETI can only constrain the parameter space it actually explores. This is why expanding the search space is crucial. We need to observe more stars, more galaxies, more frequencies, for longer durations, with greater sensitivity. We need to search for signal types beyond simple narrowband emissions, complex modulations, irregular transients, optical signals, infrared anomalies. We need to consider unconventional SETI, looking for things like atmospheric pollution on exoplanets, megastructures dimming stars, waste heat from advanced technology. The more comprehensively we search, the more confident we can be in our conclusions, whether those conclusions are detection or continued non-detection. Current data suggests technosignatures are either rare or subtle. Civilizations might not broadcast the kind of prominent, easy-to-detect signals early SETI researchers hoped for, or they might exist but be few enough and far enough apart that the odds of us happening to observe the right star at the right time are still very low despite our efforts. Conversely, civilizations might be surprisingly common, but technologically convergent. All advanced civilizations might discover that certain communication methods are optimal and universally adopt them, methods that don't produce detectable signatures from interstellar distances. The data also tells us about fast radio bursts and natural phenomena. The thousands of fast radio bursts catalogued have taught us about neutron star physics, magnetic field evolution, the intergalactic medium, and high-energy astrophysics. Even without finding aliens, the search is advancing science. Every null result, every natural explanation found for a mysterious signal adds to our understanding of the universe. SETI is astronomy, and all astronomy teaches us about how the cosmos works. The future of detection. The next decade promises revolutionary advances in our ability to detect signals from space. Multiple next-generation observatories are under construction or in advanced planning, each offering capabilities that dwarf anything currently available. These new instruments will dramatically expand the scope and sensitivity of searches, potentially finally tipping the odds in our favor. The Square Kilometre Array, or SKA, is the most ambitious radio telescope ever conceived. When complete, it will have a total collecting area of approximately 1 square kilometer, distributed across thousands of individual antennas spread over vast distances. The SKA has two main components. SKA Low, located in Western Australia, will observe low radio frequencies from 50 to 350 MHz using 131,072 antenna elements grouped into 512 stations across 65 kilometers. SKA Mid, located in South Africa, will observe from 350 MHz to 15.4 GHz using 197 dish antennas, incorporating the existing 64-dish Meerkat array and adding 133 new dishes. The SKA's sensitivity will be unparalleled. It will be 50 times more sensitive than any existing radio telescope and able to survey the sky 10,000 times faster than current facilities. For SETI, this means detecting vastly weaker signals from far more distant sources. Radio transmitters that are currently too faint to detect from neighboring star systems would become visible from hundreds or thousands of light years away. The SKA could detect signals equivalent to Earth's strongest military radars from stars tens of light years away and more powerful transmissions from across the galaxy. The SKA's design inherently supports SETI observations. Its enormous field of view means it observes thousands of square degrees of sky simultaneously, monitoring millions of stars in a single observation session. Its digital beam-forming capabilities allow it to point multiple independent beams at different targets at the same time. This is perfect for commensal SETI. Use some beams for conventional astronomy while dedicating others to searching for techno-signatures. The SKA's data rate will be staggering, processing exabytes of data per year, requiring advanced artificial intelligence and machine learning to analyze. The first phase of SKA construction is underway, with initial observations expected in the mid to late 2020s. Full operation is planned for the 2030s. When fully operational, the SKA will conduct the most comprehensive SETI survey ever attempted, potentially observing 1 billion stars or more over its lifetime. If civilizations broadcasting at detectable power levels exist anywhere in a substantial fraction of the Milky Way, the SKA should find them. The Next Generation Very Large Array, or NGVLA, is another transformational project. This will be an array of 244 radio dishes located across North America, from the southwestern United States to northern Mexico to central Canada. The NGVLA will operate at frequencies from 1.2 to 116 GHz, covering wavelengths from centimeters to millimeters. It will have 10 times the resolution and 100 times the sensitivity of the current VLA. For SETI, the NGVLA's high frequencies are particularly interesting. Most SETI searches focus on lower frequencies because those propagate better through interstellar space and there's less human-generated interference. But higher frequencies allow more information bandwidth and more precise targeting of signals. If civilizations use millimeter waves for communication, perhaps taking advantage of atmospheric windows on their planets, the NGVLA would be ideally positioned to detect them. The NGVLA's high resolution also makes it excellent for identifying the exact location of signal sources, potentially pinpointing which star or even which planet a signal originates from. China's 500-meter aperture spherical telescope, FAST, is already operational and is the world's largest filled aperture radio telescope. Its enormous collecting area makes it incredibly sensitive for certain observations, and it has active SETI programs scanning nearby stars and searching for transient signals. FAST complements Western facilities, observing parts of the sky not visible from the Northern Hemisphere and providing independent verification of candidates detected elsewhere. Optical SETI is also advancing. The new generation of extremely large optical telescopes, including the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, will all have capabilities relevant to technosignature searches. With their enormous light-collecting power and high-resolution spectrographs, they could detect laser pulses from other star systems or identify atmospheric chemical signatures that might indicate industrial pollution on exoplanets. Optical SETI piggybacks on exoplanet characterization observations, examining spectra of distant planets for absorption or emission lines that don't match natural explanations. The search for technosignatures is expanding beyond electromagnetic radiation entirely. The breakthrough initiatives have launched Breakthrough Watch, a program to image exoplanets directly and study them for signs of technology. Extremely large infrared telescopes might detect waste heat from advanced civilizations, the inevitable byproduct of energy use predicted by thermodynamics. Space-based observatories could search for anomalous infrared signatures around stars that might indicate Dyson spheres or other megastructures capturing stellar energy. Gravitational wave detectors, like LIGO and the future space-based LISA, might detect signatures of ultra-advanced engineering. Artificial gravitational waves generated by civilizations manipulating black holes or neutron stars, or the gravitational signatures of spacecraft using exotic propulsion systems. These ideas are speculative, but they represent expanding search spaces, new ways to look for evidence of intelligence beyond simple radio signals. Artificial intelligence will be central to all these efforts. The data volumes from next-generation observatories are beyond human analytical capacity. The SKA alone will generate more data in a single day than the entire history of radio astronomy combined. Analyzing this flood requires automated systems, machine learning algorithms that process data in real time, identify candidates, prioritize follow-up observations, and alert human scientists only when truly exceptional signals appear. These AI systems will improve continuously through experience, learning to distinguish interference from genuine anomalies with ever greater accuracy. Real-time detection networks will link observatories worldwide. When one telescope detects a candidate, the network instantly alerts others, coordinating simultaneous multi-telescope observations. This distributed confirmation system addresses one of SETI's greatest challenges, verifying transient signals before they disappear. With telescopes spanning the globe, at least some will always have visibility to any source, providing continuous coverage and rapid response. Citizen science will continue to play a role. Projects like SETI at Home pioneered distributed computing for SETI. Future initiatives might engage millions of people in tasks AI struggles with: pattern recognition, anomaly identification, creative hypothesis generation. Human intuition and creativity complement machine learning's computational power. Together, they form a hybrid intelligence greater than either alone. The future of SETI is not just about building bigger telescopes. It's about smarter searches, broader wavelength coverage, creative signal types, and international cooperation. It's about recognizing that technosignatures might be subtle, requiring careful analysis rather than obvious beacons. It's about expanding from radio SETI to pan-SETI, searching across the electromagnetic spectrum and beyond. It's about learning from every null result, using negative data to refine strategies and focus resources on the most promising approaches. Perhaps most importantly, the future of SETI involves sustained effort. The universe is vast. Stars number in the hundreds of billions in our galaxy alone. Even if civilizations are common, finding them might require searching millions of stars over decades. This requires commitment, long-term funding, career paths for SETI researchers, infrastructure that operates for generations. The payoff, contact with another civilization, would be among the most profound events in human history. But achieving that payoff demands patience, persistence, and the willingness to continue searching even after countless disappointments. Standing here in late 2024, looking back at decades of SETI research and thousands of detected signals, we're left with an intriguing paradox. We've heard a lot, we've learned a lot, but we haven't found what we're looking for. The signals keep coming, flagged by ever more sensitive instruments, analyzed by ever more sophisticated algorithms, and almost always explained as natural phenomena or interference. The few that resist explanation tantalize us, but without confirmation, without repetition, they remain question marks. The WOW signal still haunts us after 47 years. BLC-1 from Proxima Centauri seemed so promising before analysis revealed it was likely interference. The 8 signals discovered by Peter Ma's algorithm looked compelling, but vanished in follow-up. Thousands of fast radio bursts blaze across the cosmos, probably natural, but retaining that tiny sliver of possibility that maybe, just maybe, some are artificial. Optical transients flash in stellar spectra, unexplained but probably not laser beacons. The data accumulates, the mysteries deepen. The answers remain elusive. But this doesn't mean SETI has failed. Discovery in science often requires enormous effort, with no guarantee of success. The search for gravitational waves took decades and enormous investment before LIGO finally detected them in 2015. The hunt for the Higgs boson required building the world's largest particle accelerator. The identification of exoplanets demanded inventing new techniques and persevering through early false positives. SETI is similarly challenging. We're searching for something that might be extraordinarily rare, might not want to be found, might communicate in ways we haven't imagined, or might not exist at all. The difficulty doesn't mean the search isn't worthwhile. Every star observed without detection teaches us something. Every fast radio burst characterized adds to our knowledge of neutron stars and magnetic fields. Every algorithm developed for SETI finds applications in other areas of astronomy and signal processing. Even if SETI never succeeds in its primary goal, it advances science and technology in valuable ways. And there's always the possibility that the next signal detected, the next candidate flagged, will be the one that changes everything. The signals we've ignored, dismissed, or been unable to confirm are not forgotten. They're catalogued, available for reanalysis as our understanding improves and our technology advances. The WOW signals data is still examined by researchers proposing new explanations. BLC-1's observations have been studied in exhaustive detail, teaching us about interference and verification procedures. Peter Ma's 8 candidates remain in Breakthrough Listens databases, potentially to be reobserved in the future with more sensitive instruments. Even the thousands of fast radio bursts we've attributed to natural sources are continuously being reconsidered as new data and theories emerge. This is how science works. Observations don't go away. They accumulate. Today's unexplained anomaly might become tomorrow's breakthrough discovery when viewed through the lens of new knowledge. Or it might finally be explained as a mundane phenomenon we didn't initially understand. Either way, the scientific process continues, self-correcting, gradually converging on truth through the accumulation of evidence and the refinement of theories. Current SETI projects remain active and are expanding their scope. Breakthrough. LISTEN continues its observations, recently extending its program and partnering with additional observatories. The CHIME telescope keeps detecting fast radio bursts daily, building the largest catalog of these events and enabling statistical studies of their properties. The VLA conducts commensal SETI observations through the COSMIC program. FAST in China monitors nearby stars. Optical SETI programs examine thousands of targets for laser pulses. All these efforts proceed simultaneously, covering different parts of the sky, different frequency ranges, different signal types. New strategies are being explored beyond traditional electromagnetic SETI. Atmospheric searches look for industrial pollutants in exoplanet atmospheres, chemical signatures that don't match natural planetary processes. Artifact SETI considers searching our own solar system for probes or artifacts left by visiting civilizations in the distant past. Archaeological SETI examines how we might detect the ruins or archaeological remains of long-dead civilizations, extinct but perhaps still detectable through their lasting effects on their environment. The possibility that we might be alone remains a serious consideration, one that SETI researchers acknowledge even as they continue searching. If decades more of comprehensive searches with next-generation instruments turn up nothing, the Fermi paradox will press ever harder. Why the silence? Why the absence? Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technological civilizations are brief. Perhaps we're simply first, living in the early universe before most civilizations will eventually arise. Perhaps aliens exist, but are so different from us that our searches are fundamentally misguided. Or perhaps the universe is full of signals and we haven't learned to hear them yet. Radio interference might be blinding us to genuine signals that are there if only we could filter out the noise more effectively. Our signal processing might be inadequate, missing modulation schemes or signal structures that don't match our assumptions. Our observing strategies might be flawed, looking at the wrong stars, wrong frequencies, wrong times. The answer could be in the data we've already collected, waiting for new analytical techniques to reveal it. This uncertainty is uncomfortable, but also exciting. SETI operates at the boundary of knowledge, asking one of humanity's deepest questions: are we alone? Every observation, whether it detects something interesting or nothing at all, pushes that boundary a little further. We're exploring the unknown, and exploration inherently involves uncertainty. The payoff, should it come, would justify every hour of telescope time, every petabyte of data analyzed, every candidate investigated and explained away. The search for extraterrestrial intelligence is ultimately a search for context. Where do we fit in the universe? Is intelligence common or rare? Are we the first technological civilization in the galaxy, or one among millions? The answers will profoundly shape our self-understanding and our future. If we discover we're alone, that knowledge carries its own weight and responsibility. We might be the only conscious observers, the only minds capable of understanding and appreciating the universe, a singular emergence of complexity and awareness in an otherwise unconscious cosmos. If we discover we're not alone, that other civilizations exist or have existed, we join a larger community, a cosmic context that dwarfs our parochial concerns and opens possibilities we can barely imagine. So the search continues. Telescopes observe, algorithms analyze, scientists interpret. New signals are detected daily, added to the growing catalog of things we've seen but haven't yet understood. Most will be explained eventually. Some will remain mysteries. And maybe, possibly, hopefully, one will be the signal that finally breaks the silence, the unambiguous detection that confirms we're not alone, that somewhere among the billions of stars, someone else is looking up at the night sky and wondering if they're alone too. Until that moment comes, if it ever does, we keep listening. We keep searching. We keep refining our methods and expanding our scope. We honor those initial 72 seconds in 1977 when Jerry Eman wrote, "Wow," and every moment since when someone detected something strange, something unexpected, something that made them wonder. Those moments of wonder, those questions that drive us to point our telescopes at the stars and listen for answers, those are what make the search worthwhile regardless of the outcome. The universe is speaking. It's always speaking, in the radio whisper of pulsars, the energetic shout of fast radio bursts, the quiet background hum of hydrogen clouds and distant galaxies. Most of what we hear is natural, the electromagnetic voice of physics playing out across cosmic scales. But somewhere in that cacophony, there might be another kind of voice, an artificial signal, a deliberate transmission, a message, and we're listening with ever better ears, ever sharper attention, ever greater determination. We've received thousands of signals. We've ignored most of them for good reasons. They were interference, or natural, or too ambiguous to confirm. But we haven't ignored the possibility, the hope, the search itself. That continues, will continue, must continue, because the question is too important to abandon, and the answer, whatever it is, too valuable not to seek. So here's to the signals we've detected and the signals yet to come. Here's to the searches underway and those we'll launch in the future. Here's to the scientists who dedicate their careers to listening, to the engineers who build our instruments, to the algorithms that sift the data, to the citizens who contribute their time and computers. Here's to every human who has ever looked at the stars and wondered what's out there. The search for extraterrestrial intelligence is our search, humanity's collective effort to understand our place in the cosmos. And who knows? Maybe while you've been listening to this, somewhere in the data streaming from a radio telescope, an algorithm just flagged something interesting. Another signal, another candidate, another question mark waiting to be investigated. Most will lead nowhere, but one day, maybe today, maybe tomorrow, maybe decades from now, one will lead somewhere extraordinary. And we'll be ready. Thank you for joining me on this journey through the signals we've received from space, the mysteries they present, and the search that continues. If you enjoyed this exploration of one of astronomy's greatest questions, please consider liking this video and subscribing to Nebula Nights. Your support helps me create more long-form, in-depth content exploring the wonders and mysteries of the universe. Until next time, keep looking up, keep wondering, and keep listening to the whispers of the cosmos.